exact same thing. Arima 0 of 0. There is no R part, there is no Ma part. There is only the I part there. So what? Okay. So this is what we did. Okay. So let's see the ACF and PACF. I did the differencing. So that's the first step. Apart from looking at the basic plot and all those things and to understand what's going on, the first step is differencing because it is not stationary. If it is not stationary, you stationarize. I stationarized it. I am looking at ACF and PACF. This one I have to ignore the zero lag, but I do see that there are significant lags at specific periods. Okay, ACF, this is not decaying. Okay, there are specific time periods. There is something. PACF also is showing the same thing. PACF has some more stuff going on here. There is a bit more start of decay there. Okay, so maybe. So this is where your subjectivity comes in. You try to build multiple types of models, see which one works better. So here I know there is seasonality. So left. So first thing, instead of getting a non-seasonal difference, I will go back to my original data and I will get a seasonal difference. Because when I undifferentiate, if I already differenced it and then I do some seasonal differencing, some of the seasonality effect might be lost. I don't want the seasonality effect to be lost. So first I get a seasonal difference so that remains there. Whenever I do the integration part, the seasonal difference will come back in. Okay, so seasonality will come back in. So that's something that I can do. Did I do that? Yeah, the difference somewhat stated, but from seasonal lags, when you see these significant lags at certain time periods, not continuously, but on the 12th lag, on the 24th lag, on the 36th lag, then you know that there is a seasonal effect there. So there is a seasonality. So what we will just do is go back to the original data and now I will do a seasonal differencing. What is seasonal differencing? January minus the previous January, not January minus December. That is what non-seasonal difference. But I am doing seasonal differencing. I just difference from the previous season. That's what we will manually not do that, but that's what is happening. Seasonal differencing means January minus the previous January, February minus the previous February. So that's what we will do. So perform seasonal, yeah, I have written it there. Today's minus 12th day, or this minus the 13th, T1 minus T13, T2 minus T14. So now what is the Arima model? No, this is the Sarima model. Because I have now brought in seasonality. So I am not doing anything with the non-seasonal part. I have only done original data and seasonal differencing I have done. And the data looks like this. Seasonally different data looks like this. Now I am plotting ACF and PACF. Think about it. I am saying so many things, but I am doing only one thing. I am differencing and then I am checking ACF, PACF. This is all I am doing. Nothing more than that. So ACF, PACF, if I check, well, this is how it looks. The ACF is decaying. PACF, first lag is very strong, cuts off. But then, at a 12th lag or something, again there is a strong lag. Okay? Okay? So there is a strong positive correlation left here. That's what we saw with the ACF, PACF of strong trend. ACF decays, PACF is a strong. So now when there is a strong trend like that, I can either build an AR component into that thing, or I can do a non-seasonal difference on top of the seasonal difference. Both of them. Now you build two different models and see which one works better. Either one can be done. You can either incorporate. It suggests that this is an autoregressive term left over in the seasonally different data. There is an autoregressive term. You can try doing a non-seasonal difference on top of the seasonally different data. data or add a auto regressive term. So I don't know what I have done. Okay, what I did is non-seasonal difference. So seasonally difference data, that data I have taken, and then difference. This value minus the previous value. This one is previous value. Okay. So now I have an ARIMA 010 model. This is how the data looks. ACF again, every time I do something, I check for the ACF, PACF to see if there is any trend or seasonality still left over. Then I will add that component in again. Okay. Now I see. Okay, the zero flag is not important. Well, I see that there is a significant flag here. The first flag is significant in ACF. First flag is significant in PACF. But then there is a 12th time period. There is a seasonality still left over. There is still some seasonality left over. So now I think of model. What do? I have what is the previous model? 010, 010. So now I see, if I look at this, what is that? AR term or an MA term? If I look at PACF, auto regressive or moving average? Auto regressive. We look at auto regressive. The regression model we built for PACF now. To get PACF partial autocorrelation values, we built a regression model. Just think of that AR P from PACF. AR term from PACF, moving average term from ACF. So first lag is significant, so I need to add one AR term. But here also, this is also showing a lag. So I need to add a moving average term also. And I see that at a seasonal period also there is a significant lag. So, and here the rule of thumb is, if the seasonal period autocorrelation is negative, you add a seasonal moving average. Done. If the seasonal period thing is positive, autocorrelation, you add a seasonal autoregression. Done. And in no model, again the rule of thumb, should you have both a seasonal moving average and a seasonal autoregression. They just talk to each other too much, basically. This is too much of stuff. You should not have that many components in there. So, of course, if you build it to multiple lags, you will be able to see actually. You only look at seasonal values to see if they are decaying or if they are cutting off. Here I have only 20 lags now. If I did a lot more lags, you will see that seasonal moving average would show that ACF will cut off after this time period. In the next time period, maybe significant, maybe not. PACF, maybe it will go on before it closes. Only looking at the seasonal values themselves, if they are decaying or not. Not looking at consecutive values. So I have to now add three terms here. I had ARIMA 010, and AR one term here, a moving average one term here, and because this is negative, I add a seasonal moving average. The negative autocorrelations are indicated that they indicate that you have over difference the data. And to account for that, you add a moving average to get rid of some of that over differences. If there is positiveness, positive autocorrelation, it shows that you have under differentiated, you have not differentiated enough. So add a auto regression to take care of whatever has not been taken care of by the differentiation. That's the thought process whereby they say moving average term is negative for the seasonal period, then you use a seasonal moving average component. If it is positive, use a seasonal auto regression instead. So if if this value at the seasonal period had been positive, I would add 1 here instead of 1 here. So this would have become 1, 0, 0. Okay? So this is what my ARIMA model is, final model. This is how I built it. What I do is, initially I check for the process, what is there. Seasonality, etc. is there. We have done a seasonal difference first. There are people who will do a non-seasonal difference first. So there are no set rules here. You have to just build multiple times. But ideal, better way is first do a seasonal difference if there is a seasonality, because you want to preserve the seasonality in there and not get rid of some of that by other differences. So keep the seasonality there. So first do a seasonal difference and then check if there are still significant ACF PACFs. Try either just adding the autoregressive term or non-seasonal difference, and then check if there are ACF, PACF, if there are still some things left, build them on. So essentially in a 2 or 3 step we have done this. I have gone through the 8 steps like that, but essential steps are 2 or 3. Difference, look at ACF, see if there is anything left from trend and seasonality in conflict. At the most, 2 differences. The rule of thumb also, do not have more than, never have 2 seasonal differences for sure. Don't have 2 seasonal differences, and never have more than total 2 differences. You can have 2 non-seasonal differences if ever there is a need, but otherwise, this is the maximum. So, there are anyway restrictions, enough restrictions, you can't really play with it. And at some point you can just say, oh, well, why do I want to do all this? Let me just do 1, 0, 0, 0, 0, 1, 1, 0, 1, about 4 or 5 or 6 combinations and see what comes best. Nothing wrong, I mean, I am already putting restrictions. Oh, don't have too many lags because the equation becomes too crazy, and anyway, data in much past history is not going to affect, so I cannot have lags that are too large. So there is another rule of thumb that says all the P's and the Q's combined, this P, Q, P and Q, you should not have more than 4 or 5 terms. With so many constraints I have put, well, you can actually try out randomly all these things. In fact, after taking you through all this pain, I will show you one function which actually does all this. Okay. Finally, I selected this model. So how do I run ARIMA on that? So I have fun with a couple of slides. Step by step ARIMA model building. I have given all the steps here also in R code. So take a look. ACF, PACF. There is this comments. So comments also I have written. So won't have a problem. Let me just run through this. Yes. Okay. So here is what you have to do. ARIMA. How do you run ARIMA? If you are manually doing an ARIMA. That's what you have to do. ARIMA is a function with a capital A. There is another function with a small a. You are advised not to use that because it doesn't give all the outputs necessary for forecasting. You might just build a model, but you will not be able to forecast with that. Okay? So there is a small a ARIMA also, but use the capital A. Okay? And why is time series? And what is it? How do I specify the model that it needs to run? I said 1, 1, 1 is the order, and then the seasonal order is 0, 1, 1. Okay? And another thing, drift is not included if you have 2 differences. 2 or more different 2 differences, and it doesn't include the drift anyway, even if you say included it more. Okay, ARIMA here. Okay, so we ran the ARIMA model. ARIMA 111, 011, 12 is the time period. And how many coefficients will I have in the equation? In the equation I will have 3 terms. There will be a one autoregressive term, beta 1 times lag 1 is one variable, no? Plus theta 1 times the error 1 error from moving average of the errors, and plus seasonal moving average. So this is autoregressive curve, this is moving average curve, that is the coefficient, that is the standard error. If I want to ask you what is the t value, can you get me the t value? You thought you were done with all this. They are not doing it, but I am just asking. If I were to ask you what is the t value, coefficient by standard error, this divided by this. So, is that significant? Yeah, more than 2.5 or 3. Yeah, so it will be significant. 95% confidence interval or 5% significance. 2 is the thing, no? 2 standard errors. 95% data. So this is more than that. Significant anyway. So standard errors are not huge, so they are okay. But we use AICC value 6094.99. That's what it is. So if you build multiple models, see which one has a lower AICC. Take that. But even more than that, forecast on the testing data and see which one works better. That's the ultimate test. Okay. And finally, once the model is built, I want to check if the residuals are random or not. That's the final test now. I've got my parameters equation, my coefficients I have calculated now. After estimating identifying the model, using those differencing and then getting ACF and PACF, and then I have got the parameter estimation. Finally, the residuals I have to check for. So residuals, ACF and PACF. Let's see that. Okay, the first one to be ignored. Well, pretty nice. There is at the 15th lag something is going on. But whatever is going on, something is still going on. But everything else is nice. 15th lag, I don't even know what the significance of the 15th lag is. 12th I can understand. So something, but this is fairly random. If you don't want to believe that, if you are that concerned about this thing, there is a statistical test for checking about the residuals and to see if they are random or not, and it's called a box test. Our fellow box is not presenters. In fact, it's called Box-Ljung test. Some people call it L-Jung, but Ljung, L-J-U-N-G. And you don't have to do this, but if you want to do this, it is possible. I'll talk about it in the slide. And then start forecasting. Let me, while I am at this, let's forecast with R, with ARIMA, plot it, and that's what the forecast looks like. We will have to just see what the errors are. Okay. ACF and PACF. So main things first in ARIMA model, just simplify, keep it simple. Main thing first, estimate a model, a rough estimate of the model by looking at ACF, PACF. See if there are trends and seasonality, etc. Look at ACF, PACF. Once you have seen that, if you see some seasonality, do a seasonal difference. On the seasonal difference data, look at ACF, PACF to see if it is random. If everything is random, you are done. ARIMA 000-010 model. Done. But if not, if there are still some signatures for the trend and seasonality left, then see if you want to add a trend component there or if you want to do another non-seasonal difference. But don't do any more differences. We did a non-seasonal difference. Then we checked. And once we had seen that, we still found some signatures. ACF and PACF. There was no decay anymore. What we were saying was there is one lag in PACF that was significant, the first lag in ACF that was significant, and at the periodic, the 12th period, there was a significant lag. So now I add those three terms. There is autoregressive term 1, there is 1 from PACF, P from PACF, then Q from ACF, 1 moving average term, and 1 because the period, the lag at the period was negative, significant. I added seasonal moving average. If it had been positive, I would have added seasonal autoregression. Done. And then I check. So and then I run the model to get my coefficients or whatever, so that I can start forecasting. But then I also check for my residuals to see if they are all taken care of or not. And they are. By this time they would have been taken care of. If not, now start making P and Q by +1. So instead of 1, 1, 1, let me just make it 2, 1, 1. See what happens. Or 1, 1, 2. You just play with those and you will do pretty much that. Okay. The residuals are white noise, so you can get started with forecasting. Any questions? Okay. And I said Box-Lyon test. Okay, if you want ACF, PACF, looking at that visually good enough. But if you want to do statistical tests, there is a Box-Lyon test. There are Box-Pierce tests, multiple tests available. Box-Lyon is the most famous, and there is an equation for that where autocorrelations come to play. But Box-Lyon test, the Q statistic, the final alphabet I will teach you. Beyond after this, I won't teach you any more statistical alphabet. Q stat. These are P, T, Z, F, I, as hypothesis test, the test statistic, Q. Okay, that Q statistic is chi-square distributed. So it is distributed as chi-square with how many degrees of freedom? The degrees of freedom, there is some rule of thumb given there as well, with certain degrees of freedom, and the p-value is there. So p-value is 0.6. What do you mean by that? What do you decide? Cannot reject the null hypothesis. What is the null hypothesis? Null hypothesis, I don't know. I just cannot reject. Whatever the null hypothesis is, I cannot reject the null hypothesis. Which is good. At least you know how to deal with p-values. Okay? P-value is more than 0.05. I cannot reject the null hypothesis. What is null hypothesis? You tell me. What are we checking for? We are checking for if the residuals are all random, which means autocorrelation is equal to 0. Your null hypothesis says that all the autocorrelations are equal to 0. No significant autocorrelations left. So you do that, and yeah, you cannot reject the null hypothesis. Autocorrelations are all 0. This is randomness, so that's what it should be. Okay, right? It is random. White noise. Great. Yeah, you keep taking a look at ACF and PACF. Don't do this. Okay. And start forecasting. And we forecasted with this model. We got something. And I will show you the results. But then, so what we have done so far is we actually plotted the data, ARIMA in practice. Plotted the data, looked for unusual observations, patterns, and then we actually difference the data and looked at ACF, PACF, and then used AIC to find the best model and then residual checks. And if everything was fine, we started doing forecasting. But you want to go this way? Do you want to go this way? This way. Okay. Use auto.arima. Okay. Yeah. Use auto.arima to find the best ARIMA model for your time series. Okay, let me show that. Let me show what auto.arima is, and then I'll explain what it's doing. Miles auto-arima, auto.arima time series, and what do you want to use, AIC or BIC or whatever. That's it, auto.arima. You run that, and that's it. Wow. After all the pain, whatever we went through, did it. But it's always good to know because it's not necessary. Obviously, they have worked very hard to build this function, so it will be hard to treat it, but it doesn't mean that that really is the best thing. I mean, you can try to tweak it and see you can do better. It will be difficult because otherwise, why will people use this? But auto.arima found this 101011. So, see, when I said we have to make a decision whether I want to add a non-seasonal difference or an auto-regressive, we said, okay, let me try non-seasonal difference. I did that and then I saw and we ended up. But what if I had added an auto-regressive term directly? Maybe it would have become random automatic there itself. So maybe that's what happened here. Okay? So that's what this so it's a slightly simpler model. Just one difference in term we have extra in our manual manual. Yeah, the errors are small. Fine. AIC is actually slightly more. 6,123. Our AIC was 6,094 or something. Actually, our AIC was better. We'll see. We will forecast and see who is better. And then there is the forecast. Forecast dot arima. I run the same thing and plot it. Obviously, that's the auto arima output. Forecasted data, and that's about it. And then we will show you another one more down, and then we will be done. Okay, auto.arima. So what is auto.arima really doing? Just for you to understand that it's a very fairly subjective step-by-step kind of thing. Auto.arima was written by function by Professor Heinemann and Hunter. Heinemann, he has a book, Otext.org, it's right here. Very nice book if you want to refer to any time series related concept. This is one. I will show you one more link after this. I think those two are good enough. There may be another one, two or three, but these two are more than enough. So don't ever go beyond that. Very nicely written text. The entire text is online actually, but there is no Indian version of textbook to buy. It's expensive one, but they have not. I don't think any bandwidth stuff. So it's a HTML based thing, and that book is available. So what they do in auto-arima, find D for stationarity, do the differencing, and then P and Q are selected using a stepwise approach, one after another, and see which one minimizes. And what they start off with is 4 different types of initial models. Arima 2, D2, D can be 0, D can be 1. Arima 0, D0, Arima 1, D0, Arima D0, D1. So there is one auto-regressive term here versus there is one moving average term. This is only differencing, no moving average, no auto-regression. And here 2 and 2. This is probably the most complicated unnecessary stuff. If D is equal to 0, they add a constant and intercept also in the equation. If D is not equal to if greater than or equal to 1, then the model refuses to add an intercept. Okay, it doesn't take it. Then, once you have done that, P and Q, 1 by 1, plus 1, minus 1, plus 1, minus 1, run the model, check it. That's what internally auto.arima is doing. Will that be better? Maybe. And check for AIC. And whatever minimizes the AIC, fits that as the final model. In fact, even constant, the drift, include the drift, true, false. But if D is differencing is more than 1, even if you include it, it will kick it out anyway. So that's how it goes through various models in auto.arima. Changes P and Q plus 1 minus 1 from the original models. Checks for the AIC. Only goes by the AIC. Whatever makes the AIC minimum, it picks that. That's what it is. Okay? So that's what auto.arima is. And it does a decent job, stepwise approach. So our model, this was auto-arima model. We have lower standard errors compared to our model. This was the manual arima we built. But we had a lower AIC compared to that. So, and both of them not very complicated models. It has 1, 2, 3 terms. We also have 3 terms. We just had a level of difference in extra. And so, we have done these things. Our forecast with Arima, auto Arima, this was auto Arima. This is the old winters. And so, what I did is, I actually calculated the make manually in Excel. Excel is shared with you, it will be shared with you. I am comparing the mean absolute percentage error for all these models. I have old winters model, I have manual Arima, and I have auto Arima. And I am trying to see, I have done a forecast for 36 months. I am looking at the performance over a 3-month forecast, 6-month forecast, 1 year, 1.5 years, 2 years, and 3 years. Okay? I have just the same data I have plotted here also. Auto Arima, by far the best. It has done the best. From 3 months all the way to this thing, the mean absolute percentage error is the lowest. Manual Arima, actually we were doing close enough to auto Arima, and up to 20 months or so, certainly up to 1.5 years, our model did better than old winters also. Beyond that, old winters has a pretty much average here. Pretty reasonable. But even otherwise, look at the numbers. 1%, 1.5% at the most. At the most, it is 2% really. Error for almost 3-year horizon. Even 3-year horizon, manual Arima messed up, but auto Arima 1.6%. Old winters 2%. 3-year forecast, not bad. Just for running a one-line code, auto.arima. First, get the data, convert it to time series, PS, and then run auto.arima. 2-line, done. No, actually, last 17 years. I use 17 years, okay. In fact, now you can start thinking about improving that. Now I have enough data, and I know that 911 has messed up something there. I get rid of the data prior to 911 and start after that. It might actually improve it. So there is enough to think about improving the model. This was with almost no effort. That's the beauty of these models. Almost no effort, and I am getting a really nice model explaining these things. So that's a time series model. Some more rules, tons of rules for identifying Arima models. Duke website has a very nice coverage on time series models. So Duke website that other guy, Professor Heidler book. Just take a look at those. I think Penn State also is a reasonable one, but I think this should suffice. Finally, let's do one case in 5 max 10 minutes, and that will be it. So forecasting sales of some tractors. I will introduce a new application here that we have not talked about. We talked about it during linear regression, but I will now show what's going on here. Very important. Okay? So I have the tractor sales data. This is it. Okay. So first step, I get the data, I convert it into time series, I plot it, I can even decompose it. But you see, this is what it is. What does that tell me? The seasonal trend is increasing. So a multiplicative model, if I have to use board printers or something, multiplicative would be a better thing here. Okay, this is not what we saw. Okay, great. Now some excitement there. But what happens? I am decomposing it. Nice trend. There is a beautiful trend. Nice seasonality, but something is randomness is there is still some not as random. Okay. So what do? I don't have to do anything. This is fine. Decomposition just to understand that. But I difference the data. That's the first thing we do. Difference in the data. This is how it looks. The mean is constant. Variance is not constant. So it has not become stationary. These kinds of things, how do I deal with them? I do some data transformation first. Okay? Data transformation, what do I do? Log transform. Log is the best, the first thing that you should try in data transformation. Log transform. This is the log transform data. Now your seasonality has stabilized, no? Pretty constant. Straight line here, nice, beautiful, and then, oh, this is pretty. So now what do I do next step? Difference. Difference the data has. How many things can I do? I do difference and then I check ACF, PSF. In all of these, that's all we are doing. Difference to make it stationary. If it is not stationary, make it stationary. Then do ACF, PSF on the stationary data. See what signatures are left. That's it. That's all we do. Data transformation, if I have not been able to stationarize it, if that thing is just going on, or a whole printers model if I use the multiplicative method. You can try actually the regression on time methods. This is pretty decent actually. Using multiplicative seasonality. That should also do a good job on this data. It looks pretty good. So I log transform the data and then I get difference. Difference on the log transform data. This is now pretty stationary. Mean is constant, variance is also constant around that. Auto or even no. So auto or even will not do that. The transformation you will have to do. I think I'll show the R code as well. I have done it on both also as well. But you have to. I don't think auto or even will do that. It starts only with PQ and the difference is, but it doesn't know how to handle the transformation of the data. Maybe someone has to think about writing the function. Should be doable. Check for variance. The mean is constant, variance is not constant. Include a log transformation in the data. See that? I think most of the time with log transformation takes care of it. You create a new function. You are doing. Why not? Okay, so now I do ACF, PSF. That's the only thing I do after differencing. Well, so this is cutting off, this is cutting off. So there is actually a bit more stuff happening here. So this has a cleaner signature than this one. This has some other stuff going on. The first one is anyway useless. The 12th period, this is the 6th flag and the 18th flag. The 12th flag is there. 12th flag, so there is a seasonality. I know there is a seasonality. Okay? So now, what do? I can, so PSF has some decay, but ACF cuts off, so some moving average, but there is a strong seasonality. Okay, so I do auto or even. with that. But auto arima is giving me 0, 1, 1, 0, 1, 1. See, it has only the moving average and the seasonal moving average term. That's all there is. Okay. And this is the log transform data. And once you have that, you look at the residuals. Zero lag is important, not important. Well, beautiful. All the residuals are taken care of. Auto arima built a model, and I am looking at the residuals. Perfect. Taken care of. Done. Now start forecasting. Fox swim test, if you want to do that, also shows 0.34. That means you cannot reject the null hypothesis. What is the null hypothesis? Correlations are there. They are random, so correlations are all equal to 0. Okay, and then I start forecasting. This is my forecast for the next 3-4 years. 3 years. We have not yet seen them if we get the data. But see, this is still in the log data. If I want to do it in the actual data, I need to unlock that. Anti-log. Okay. So let me show the data for this thing. This is the last slide anyway. Let me show the data. Let me show the steps. So here is the tractor data, and we decompose, we saw all that. N dips. What do you think N dips will give you? One. Plot the difference in tractor sales, okay? And so we have seen all this, okay? Log data. Difference of the log data, we have seen all that. Auto arima. Here, I have done auto arima for the actual data. But it's doing it still. Okay, there it is. AIC was, but AIC anyway, I cannot compare the actual data and the log data because the data has changed. But when I ran this on the actual data, auto arima, it gave me 0, 1, 0, 0, 1, 1, 0, 1, 0. It didn't account, there was no seasonality that it accounted for. So I don't think its forecast will be very good. But let's try. Only one moving average term is there, apart from 2 differences. It has done a seasonal difference, so it has got rid of that seasonality. So that's one model it has got. But the other model of the logged data, logged data, and that's the one. It has found the one seasonal moving average term also. Wow. And if I want to now forecast on the actual data, now there is an alternate method that I used to predict. So predict is another function for forecasting, predicting for 36 months ahead. On the log data, I do that. The beauty of the predict function is that it also gives the standard errors so that you can build your confidence interval manually. And I am plotting that. Now, see, this is what my original data is. Okay, this is the original data. I want to now, so 10 to the power of the predicted value, because I am getting the anti-log. Okay, so I run the anti-log. That is what we got. That was my prediction. Okay, and I want to put confidence intervals around that plus 1.96 times. The SC is the standard function in there, in the predict function. So that gives me the upper confidence level, and this gives me the lower confidence level. brings me to the end of. It's pretty nice. So all you need to do is in ARIMA modeling, all you need to do is look for the pattern, what is going on, what are the processes, trend, seasonality, randomness. Look at that. Difference the data. If the difference data is stationary, start finding other signals, leftover signals, build a model or do your R1. If the difference data is stationary, it's a mean but the variance is not stationarized yet. First do a data transformation and then follow the same. Then do the difference. Auto ARIMA also makes sense. So, pretty nice powerful models. Obviously, there are many more models, but that's suffices. So, what did we cover today? Logistic regression. We started with logistic regression. Oh, that was once upon a time. Really once upon a time today. The logistic regression, but we have actually revised all the logistic regression before that. So let's not get there. People are going to torture me for the torture we gave you. So, time series. Tell me how we started learning about time series. Three important concepts. First is ACM, autocorrelation, partial autocorrelation. To get the partial autocorrelation, we just build a regression model up to the lag that I am interested in, and I take that correlation value. Okay? So lags are what are your independent variables. In any time series, lags are the independent variables. To check for whether my data is related or correlated to the previous values, previous days, previous weeks, whatever. So ACM, TSM. Then any time series has three components. What are they? Trend, seasonality, and randomness. And so that's what it is. Decompose function, decomposes. Okay. And finally, the third important concept: stationary, non-stationary. If the data is non-stationary, that means if the data is trend and or seasonality, it is not stationary. Stationary data has constant statistical properties. Constant mean, constant variance, whatever, everything constant. If it is not, there is a nice way of stationarizing it. How do you do that? Difference the data. Do difference. This value, yesterday's value minus today's value. That's it. Or seasonal differencing. This month minus the same month last year. Or this quarter minus the same quarter last year. Like that. If it's a weekly data, this week minus previous week. Whatever that might be, the seasonal factor or seasonal period, you just do that. Okay. So you difference the data to make it stationary. Good. Done. And then we started talking about model building. Yeah, simple models. So because we did regression on time models. And we found that while it was getting the trend defined, how do we handle seasonality? There are two ways. Dummy variable. In one case we said, okay, seasonality is not getting taken care of. Let's use another variable. Let's create another variable called seasonality, which is a categorical variable, which users may convert them into dummy variables. A dummy variable regression, same regression that we have learned, nothing new. The other way of incorporating seasonality, additive and multiplicative, where we actually use the regression. The trend value is forecast or predicted using the trend equation. We take the actual value, we see the difference. The difference we assume is coming from seasonality. And we take the average for each time period. In January, if I have the data for 17 years, there are 17 Januaries. Each January has an error. All those errors average, I say this is the seasonal factor for January. And then I make a forecast or prediction using the trend equation. Add or multiply depending on what I did earlier for January, that period. So, two different ways of handling the seasonality. Then we came to even simpler benchmarking models. As seasonally driven no, seasonal driving method, and then the trunk was drifting. Okay? And then we came to some smoothing models. Smoothing models, simple moving average, weighted moving average, exponential smoothing. Okay? So that's simple smoothing things. And then after that we came to voltmeters and Riemann. That's all we did. Voltmeters uses the same concept we learned, that initial trend values come from the regression on time methods. Initial seasonality comes from the dummy variable approach. Detailed math is unnecessary, but it comes from those kinds of things. And then it keeps updating with each time period as the data comes in. The smoothing, exponential smoothing. So it uses regression on time, it uses exponential smoothing, it uses the dummy variable approach for seasonality, mixes everything up, and there comes the voltmeters. And then we came to finally Riemann model. Riemann auto-regressive integrated moving average. AR is the auto-regressive model. So AR1 model is the same as Riemann 100 model. It can be called AR1 model as well. Only regression, one term, straight line, that's it. So that's auto-regressive integrated moving average models. So moving average models more applicable when randomness is pronounced, auto-regressive when there is trend pronounced. When both of them are included, ARMA, ARIMA, but we saw the ARIMA, auto-ARIMA is available, but the fundamental thing of an ARIMA, the Box-Jenkins methodology is take the data, transform if the transformation is needed, because you stationarize the data. First thing is differencing. Differencing should make it stationary. If it doesn't make it stationary, if there is still variance included, then transform the data. Otherwise, if it is stationary, now look at the ACF, PACF signatures to see if there are significant lags there. Those significant lags, so that part has to be accounted for. There is still some trend left. How do I see that? I see that from the PACF. If auto-regressive term is still left, there is the stationary thing has not stationarized everything. There is still a PACF, the first or the second lag, they are still significant. That means that much of trend is still left out. The differencing is not accounted for all of them. So I added one or two auto-regressive terms to take care of that also. No, PAC or PACF, if there is moving average, if there are one or two significant terms left in the ACF plot, then I say that there is some kind of averaging that needs to be done to take care of that leftover some other randomness or other moving average component. So we do that. Once we did that, we then run the model and get the parameters and whatever not. That's only needed for forecasting. Then I check for residuals. With that model run, the residuals should be pretty random. ACF, the residuals random means ACF and PACF should not have any significant thing. So, as long as there is a significant lag left in ACF and PACF, you have to add an AR or a moving average term or a seasonal term. If there is at specific seasonal periods, if there is a thing. If there are nothing, done. Then left over, you keep adding. That's it. So you are accounting for that. You are trying to make everything only. So you are trying to ensure that all the trend and the seasonality is accounted for in the equation. So when you check at the residuals, if they are not random, it is showing the regression term, the signature. Add a regression term. Then check the residuals again. It should have taken care of that because you added a regression term there. No, moving average term, add. Take care of it. Eventually the residuals have to become random. That's what really we are doing. AutoArima does that using AIC to find the best fit. And that's okay. That's actually what is Arima doing. Difference and then checking ACF, PACF. Anything left over, add a term. Anything left over, add a term. Till nothing is left over. Only randomness is left over. That's fundamental in one line, if I have to say, that's what it is. Great. So I think there is still some time left over for, not for me. I don't know what's the plan. You want to do it? There is a WQ.
Yes, they have to take a test, but the lab I doubt will have any time.
You won't have any time.
Yeah,
Yeah, and they don't have any energy left.
sure.
So let's do a WQ. And actually, the benefit of this whole thing is that you get to leave earlier today. Earlier, no? You normally also leave it by the tea. No. And I think the lab day is where we can have a very thorough practice on all of this. Maybe the assignment that you planned, just share it. Let people work on it. Ask questions. Activities will be shared so that you try to get your hand dirty. Maybe this is the blessing in disguise, in fact. That might be useful. And then some of you will be stuck on the first letter itself. Good, no problem. Ask questions. I think that this, and if this really works out, from next time onwards, we will make this standard. Where I teach for 7 hours. No, I think share the assignment and work on that, please. Ask questions, and on the lab day, anyway, it will be repeated and other problems will come. Thank you very much. I'll enjoy the rest of the program. But the main thing is that if you are thorough with these 8 days,